Hello everyone, this is Kyle Welch with RCR Wireless News. I want to thank everyone for attending today's webinar, VoLTE, Don't Risk Short-Circuiting Voice, presented by JDSU. Our presenters today are Paul Gowans, Solutions Marketing Manager at JDSU, and Steve Barnes, Product Manager for VoLTE IMS at JDSU. At this time, I'd like to pass the presentation over to Paul.
Thanks, Kyle, and thanks everyone for joining us today. So the focus is around VoLTE. I think everyone knows that delivering voice services in an LT environment is a major goal of operators around the world. And voice has always been a fundamental service of mobile communications and will continue in the future. But it does need to adapt to social changes, the way people communicate today. And this is really where voice over LT or VoLTE comes in. It's around delivering a mobile voice service that embraces the latest technologies available and also meets the kind of growing demands of the mobile user. So this is what we're going to be covering today in a bit more detail with the kind of next hour. And we'll start off talking about kind of where VoLTE's come from and the standards, move on to the technology. We'll talk a bit about voice quality. That's a kind of fundamental area, and how you do handoffs, and then we'll cover the challenges and solutions relating to VoLTE. So VoLTE coming to a network near you. I think the landscape for VoLTE has really changed considerably over the last 12 months. It's now no longer an if, but a when operators are deploying. I think the other thing is that with VoLTE, typically messaging, or what was SMS, will evolve to IP, and it should really be the birth of a whole set of integrated applications that are based around IMS. And we'll talk a lot more about kind of IMS, which is the IP Multimedia Subsystem, because it really will be and is the central nervous system of what will be a new set of LTE IP based services. And you know, kind of where we are today, the Global Mobile Subscribers Association, GSA, they reported recently, they did an update to this, that there are about 90 operators in 47 countries investing in VoLTE deployment studies or trials. 16 operators have already commercially launched VoLTE in 7 countries. So wherever you are, VoLTE is either being deployed or planned to be deployed soon, or certainly being kind of tested in the lab in your operator of choice. So let's talk about VoLTE and its advantages. To the user, most importantly, it delivers really what I would kind of consider a kind of almost a voice plus service. So building on core communication services. So it's about faster connection times, the ability to create instant connections. It's about HD voice, superior voice quality, and you know, it's about integrating with other services like messaging, so kind of rich communication services, so voice can be at the kind of heart of that. On the operator side, VoLTE uses a much more efficient use of scarce RAN resources. It allows operators to deliver an IP-based differentiated services, as we mentioned on IMS, which we'll talk a lot more later on. It provides that kind of foundation for those higher value services to kind of integrate into voice and IMS. And importantly as well, it reduces the overall cost of delivering a voice service. And that's, of course, an important thing. So you get advantages for the user and advantages for the operator. Now, let's talk about standards. So, you know, LT was originally defined as a 3GPP project release 8, and LT standards, as we can see in here, you know, release 8, release 9, LT goes to release 9, 10, beyond. It continues to evolve. Many people think the LT was really defined as data only, but actually many of the components to support a VoLTE service were a key consideration in defining and designing LT. And voice in LT really is a media stream, albeit an important one, but is a media stream. And in release 8, as well as defining kind of always-on IP connectivity, work developed on the radio and core network to optimize the transfer of packets. In fact, IMS and VoIP encoding as well as kind of emergency call requirements were done before that, and they were continued to be adapted in release 9. Release 10 as well, whilst focused on an LT Advanced, does introduce some advanced capabilities of voice call continuity. Release 11 continues to kind of evolve that around kind of handoffs, etc. At the same time, the GSMA has been involved in the definition of standards work around delivering VoLTE. You might know about the GSMA IR92, which is about IMS profile for voice and SMS. And then there's also IR94, which focuses on IMS profile for conversational voice services. And these GSMA proposals are important because they typically are the preferred choice for mass market voice and video calling over LT today. So that's about kind of VoLTE, the advantages it brings, a little word on standards. Let's talk about the kind of network evolution and the technology evolution to deliver VoLTE. So at a very kind of high level, before we look at the challenges, some of the technologies to deliver VoLTE. This particular diagram provides a really kind of high level architectural view of a mobile network, showing some of the kind of key components that we're going to talk about in more detail. So really, there are three fundamental components that make up a whole kind of LTE Evolved Packet System, or EPS, as you'll hear. There's the EUTRAN, which is really the whole kind of RAN interface, evolved from what was the UTRAN and UMTS, so the consolidated capabilities, for example, down into the eNode B that were separated out. So you've got the EUTRAN, you've got the Evolved Packet Core, which at a kind of high level looks like this, covers the core architecture. Of course, there's a lot more components and complexity to that than we're showing here. And then this important capability, IMS, which is really the control framework for delivering IP-based services, IP Multimedia Subsystem. So really, as well as all the kind of mobility aspects around delivering voice, those are three kind of key engines that support the delivery of VoLTE. Now, underpinning LTE is this whole kind of concept of bearers. And you basically think of a bearer as really an IP data session, and by data session, of course, we're including voice, but an IP data session with a defined quality of service. And all traffic is mapped to the same bearer receiving the same packet forwarding treatment. So the defined cause is crucial here because it's the importance of how you deliver a guaranteed voice quality service. So you just think about this bearer as a pipeline connecting two or more points through which data traffic, and that data traffic can be voice, can flow. So what you see in the concept of bearers, of course, is there's to establish an end-to-end bearer from the UE, from the handset, right the way through to the packet data network, several sub-bearers have to be created. So for example, you'll connect a radio bearer up with the UE and the eNode B, must be established before you can set up an EPS bearer, for example. Now, the EPS bearer, and we'll show this in a minute, can either be default or dedicated, and it will have a defined set of cause characteristics, as we mentioned. One of the important characteristics of those is the QCI, which is down in this table here, the cause class identifier. And you'll see, for example, that you've got some guaranteed bit rates and you've got some non-guaranteed bit rates. VoLTE calling, for example, gets a QCI of 1, very, very kind of low packet loss associated with it, and specific kind of delay and priority through the network associated with that. IMS signaling, for example, but setting up the call, gets a priority 1 through the network and a kind of QCI of 5. So you'll see that's a non-guaranteed bit rate service, but a high priority one, because these are split between guaranteed and non-guaranteed. Okay, so the concept of bearers is important because it helps define how service quality is kind of delivered. And as I mentioned, there are when a UE attaches to the network, typically what happens is it gets a default bearer That's got a kind of separate IP address and a particular QCI assigned initially, typically kind of 5 to 9. But once that oh, by the way, I should say the signaling, as I think I mentioned, has its own bearers, but then dedicated bearers can be set up to provide dedicated tunnels. They don't require a separate IP address, but for services like VoLTE, a dedicated bearer can be set up to provide that level of quality for a voice service. So for conversational voice, as I said, it would be set up with QCI equals 1, so they can get a guaranteed bit rate with this priority of 2. So that's important, again, for being able to deliver that kind of voice service, getting a dedicated bearer associated with it. And then just touching on the radio bearers, I mean, the radio network, of course, is kind of fundamental to delivering a high quality voice service. And radio resource control, this RRC, is used to establish certain components of that. So there's the things like, for example, robust header compression, semi-persistent scheduling, transmission time interval. I'll mention just touching on one of those, the robust header compression. It's very important because it takes an IP packet header and strips out information that you've already established between a UA and an E node B. So if that's already established, for example, once the destination IP address is established, there's no need to keep sending it because it's a point-to-point link. So with VoLTE, which is a relatively small payload, that effect can be really significant. If, for example, you're an IPv6 network, the header reduced from 60 bytes to 3 bytes. And that's significant very much in the RAN. So there's things like that. TTI is about kind of subframe and bundling repeat requests into the same message. So these things are all there to kind of help give a more robust radio network to providing those radio bearers to set up VoLTE. Okay, so that's a bit on some of the technology. I'd like to hand over to Steve now, who's going to take us a bit more detail through the architecture and IMS. Okay, Steve, thank you.
Thanks, Paul. Hi, everyone. Thanks again for joining today. So let's take a bit more of a deeper dive into some of the technology that enables the VoLTE service to be delivered. To deliver a broadband VoLTE service, essentially 3 main parts of the network have had to evolve to make that service available in a reliable fashion. The first part of the network that's had to evolve is the access network. And this, in the evolved architecture, now essentially involves only one type of network element, and that's the evolved E node B, or just the E node B. Previous architectures such as UMTS UTRAN had 2 network elements. It had the node B and the radio access controller, and while even earlier the GSM and Edge architecture had the base transceiver station, the BTS, and the base station controller, the BSC. By simplifying the access architecture to just have the E node B, this reduces complexity in the network, it reduces latency, and it reduces costs while increasing the data throughput. The second part of the network that's evolved, and Paul has touched on this, is the EPC, the Evolved Packet Core. And here there are essentially 3 main network elements involved. First, we have the MME, which is the mobility management entity. We also have the S gateway and the P gateway. The MME is responsible for the network access stratum signaling. It's also responsible for authentication and authorization, session and mobility management, and also selecting the appropriate S and P gateways. So the MME is a key element in providing mobility from LTE to the circuit switch network, where when circuit switch fallback is required, or when single radio voice call continuity is required. And we'll touch on both of those topics of circuit switch fallback and SRVCC later in the presentation. Each handset or user equipment is connected to a single S gateway, and the S gateway is a user plane anchor for inter-E node B mobility and handover. And the S gateway also performs packet routing and forwarding and charging for roaming. The P gateway, on the other hand, is the gateway towards the packet data network, such as the internet or other intranets. And it's responsible for IP address allocation for the UE, for packet routing and forwarding, and for policy and charging enforcement. So these network elements have to work closely together to help deliver the VoLTE service. And then thirdly and finally, in terms of network evolution, there is the IMS, the IP Multimedia Subsystem. That includes multiple network elements. The main function of the IMS is service control, quality of service and IP policy control, charging, authentication, and interworking with other networks. So let's take a little bit of a deeper dive into the IMS. As you can see here, there are multiple network entities involved, multiple protocols involved, all working together to provide the VoLTE service. And as Paul said earlier, the IMS is the central control plane for not just for VoLTE but for other services also. The call session control function shown in the center of the diagram, these nodes serve as proxies and process SIP signaling. And the CSCF is split into 3 separate logical functions. The first of those, the proxy CSCF, receives all of the SIP signaling from the UE. The proxy is responsible for SIP compression, IPsec security association, interacting with the policy function, network address translation, and emergency service detection. And when a subscriber is roaming, that proxy CSCF will appear in the visited network. The serving CSCF handles registration, downloads, authentication data from the HSS, uses the service profile to determine which application server is contacted for a particular SIP request. The interrogating CSCF obtains the name of the next node from the HSS. It assigns the serving CSCF based on information about the capabilities that it receives from the HSS and routes incoming requests to that serving CSCF or to an application server. The HSS, shown here on the right-hand side of the diagram, is the central repository for subscriber information. The HSS stores location information, security information used in authentication and authorization, profile information, which defines what services are subscribed to and which serving CSCF is allocated. And then the PCRF, the policy and charging rule function, determines policy and decides on charging control based on session and media-related information from the proxy server. The PCRF plays a key role in authorizing VoLTE bearer establishment, modification, and teardown. And as Paul mentioned earlier, bearer management is fundamental to delivering VoLTE service. So we've taken a quick look at the aspects of the networks involved in VoLTE service. Let's take a look at what the call flow for a VoLTE call looks like across the IMS. In this example, we can see that the calling and called parties are actually in different networks. So starting from the top left, the handset, the UE, sends an initial SIP invite, which traverses across the home network's IMS, including the proxy and serving controllers that we've touched on earlier. The interrogating CSCF in the called network, it requests the address of the serving CSCF of the called UIE by issuing a location information request to the HSS. You can see that here at step 7. And then the HSS responds with a location information answer, which is step 8. When the SIP invite reaches all the way over to the called UE here on the right-hand side, it will typically respond with a 183 SIP session progress response while it is establishing a dedicated bearer. Once that 183 SIP message has traversed back to the calling UE, it will then send a provisional response acknowledgement message. Then once the dedicated bearer is established at the calling UE, it will send the SIP update message. And then once the dedicated bearer is established at the called UE, it responds to that update with a 200 OK message and starts ringing. It will then issue a 180 ringing response to the original invite. When the call party answers, the called UE sends a 200 OK response, and the calling UE responds to that with an acknowledgement. So at this point, the call is set up, the bearers have been established, and the two parties are able to have the conversation. That call will then continue until, in a normally terminated call, one party hangs up, and the UE of the party hanging up will then issue a bye message. That bye message causes the proxy controller and the PCRF to interact with each other, and for the P gateway to deactivate the dedicated bearers. So as we can see, there is a significant amount of control plane signaling required to manage a VoLTE call. So that's a brief overview of some of the technology that's involved in the access network through the EPC into the IMS to enable VoLTE service. Let's now turn our attention to the issue of voice quality. There are a number of factors that can impact on the voice quality as perceived by the subscriber. And some of these and some of the measurements that are associated with voice quality are listed here on this slide. So starting at the left, packet loss occurs when one or more transmitted packets fails to arrive at their destination. It only requires a small percentage of packets to be lost to cause significant impairment in voice quality. Moving along, jitter is the variation in time between packets arriving. While a jitter buffer can be used to mitigate the effects of this, human voice interaction requires very low levels of jitter before the conversation quality decreases. Delay or latency occurs due to analog to digital conversion in the codecs, buffering, different transmission times for various packets, and other factors. R factor is a measure of quality determined by the implementation of the E model, which was originally described in an ETSI report and has been standardized by the ITU in standard G107.1 for wideband codecs, which are used in VoLTE to provide high-definition audio. So while it's theoretically possible for an unimpaired wideband connection to achieve an R factor above 100, in reality that does not occur. An R factor provides a more granular measure than the traditional MOS, and mean opinion score, or MOS, has been used for decades in telephony to rate perceived voice quality. So what we've looked at so far in terms of voice quality are measures such as jitter and R factor and MOS that can be measured using passive monitoring techniques. And those really focus on the transport of the voice packets across the network. A complementary approach to that is represented by PESC and Polka that are based on active testing of the voice quality. So in this approach, it's achieved by sending defined voice samples across the network and then comparing the received sample against its reference to determine the level of impairment. So quite different from a passive monitoring approach. And as noted on the slide, Polka is the successor to PESC and is focused on higher bandwidth audio, such as that delivered in VoLTE. So let's now move on and take a look at how networks can cooperate with each other to make calls, to allow voice calls to be made or to be continued to be made when the subscriber moves outside of LTE coverage. So the first example is circuit switched fallback. Circuit switched fallback, or CSFB, enables a UE on the LTE radio access network to originate or terminate calls by falling back to the legacy circuit switch network. A key interface in CSFB is the SGS interface between the MME in the LTE network and the MSC server in the circuit switch network. The protocol that runs over SGS interface is the SGS AP, or application part, which itself runs on top of SCTP. A prerequisite for circuit switch fallback is that the UE has performed a combined EPS IMSI attachment into the serving EPS and to the circuit switch network. That attachment includes circuit switch additions, primarily achieved via location update requests from the MME to the MSC, and location update responses from the MSC back to the MME, again over that SGS interface. In a mobile originated call with circuit switch fallback, with the circuit switch fallback, first the UE sends an extended service request to the MME. The MME then sends a context setup response request to the eNode B, telling the eNode B that the UE has requested to fall back. The eNode B will then respond with a context setup response back to the MME. The eNode B then redirects the UE to interact with the MSC on the circuit switch network, at which point the UE will perform a fallback and now interacts exclusively with the circuit switch network by sending a setup message to start control procedures with the MSC. So circuit switch fallback from a control plane management point of view is a quite complex procedure, and to be able to monitor it well and to be able to be deterministic, it's important to be able to monitor across multiple protocols to be certain whether or not the circuit switch fallback attempt was successful or not. The other example of networks cooperating together is single radio voice call continuity, or SRVCC. This is a mechanism that seamlessly allows an ongoing VoLTE call to be transferred from the LTE to the circuit switch domain. SRVCC is triggered when the handset measurements of things like circuit level or other voice quality drop below a threshold, at which point the eNode B will inform the MME that a transfer is required to continue the call. The MME will pick the dedicated bearer with QCI1, since that's the voice bearer, and the MME will send a packet switch to circuit switch request message to the MSC via the SD interface. The protocol running on the SD interface is GTPC-v2. The MSC then receives the circuit switch radio, reserves the circuit switch radio resources, and sends an invite to the service centralization and continuity application server. That invite includes the session transfer number and the correlation mobile subscriber ISDN number. That number identifies the subscriber whose domain is being transferred. That number is then used to associate the incoming session to the already established IMS session. And the SCCAS then updates the other side of the IMS session with a new local descriptor having a new IP address and port number, which are now used for the user plane RTP and RTCP sessions. The SCCAS clears the signaling connection towards the UE that is moving to the circuit switch domain. The MSC then acknowledges the MME by sending a packet switch to circuit switch complete notification. The MSC performs location update procedure towards the HSS, informing it that calls and texts to the UE should now be routed via the MSC. So even compared to the circuit switch fallback, the SRVCC is a highly complex operation, but the ITU standard says that the requirement for maximum speech connection gap while SRVCC is in progress is just 300 milliseconds. So that's a look at some of the continuity services that are available in VoLTE. With that, I'll hand back to Paul.
Great, thanks, Steve. So we've had a good look at the technology behind VoLTE. Let's now look at some of the challenges that VoLTE brings and what solutions might be needed to deliver a kind of high quality service. Hopefully you've seen it's quite a complex environment, so there's a lot of opportunity but a lot of challenges associated with that. So even just looking at, for example, like the call setup, to get that quality service. So there's three areas I wanted to just kind of pick out. Pre-deployment testing. We should never underestimate the importance of rigorous testing in the lab before the users experience it, and particularly with a service like voice, and Steve just talked about some of the interoperability that needs to go on, etc. The other aspect of it, the RF considerations. So we know that the radio access network's fundamental, but there might be other aspects of how RF's getting delivered. Maybe MIMO's involved, maybe it's LTE advanced. And that RF component can have a major effect on the whole kind of end-to-end service. And then measuring end-to-end voice quality, end-to-end. It's, you know, service quality is only as good as the weakest link. And the VoLTE network, as we've seen with the kind of bearers, needs to get negotiated on a kind of hop by hop basis. So, you know, the complexity of that whole kind of control plane and user plane in setting up and delivering voice, all these aspects have to be looked at for looking at the whole end-to-end service and being able to optimize that. Indeed, just showing this kind of managing end-to-end, I tried to kind of pull out, you know, various aspects from the handset, from the UE, right the way through to the core, and some of the things that you might want to do. For example, like service testing from the handset, locate hotspots. What about the backhaul? Real-time performance analytics as well. So real-time becomes a much more important aspect of service assurance, because you've got a service which is kind of operating in real time, and the quality can vary, you know, through that service. So this, you know, given it's a person-to-person, typically real-time application, that whole kind of weakest link in the chain becomes very kind of fundamental in delivering an end-to-end high service quality voice service. So pre-deployment testing, before you deploy any service, you need to be able to test it under, and this is important, the real live conditions, simulating, emulating, you know, thousands of end users. You might need to load sites, because the loading of the site, of course, can have a major effect on you know, what service is getting delivered. You need the flexibility to change parameters, look at arrival rates, look at hold times, but being rigorous and methodical in your pre-deployment testing can make sure that you're ready to launch. And you certainly, you know, don't want your users to be your test engine. So doing that before you roll out is very, very important. And then the RF, I touched on the RF, and although the RF isn't necessarily associated with the service itself, the properties of the RF component of LTE network really are crucial. And even once the cell site's operational, maintenance and troubleshooting is needed to kind of manage and optimize that whole kind of radio infrastructure. And we touched about the RF characteristics being important to help deliver real-time, high-quality, low latency, such as VoLTE. You know, and we've got here just, you know, showing a, you know, VoLTE, you know, as we know, is really a data service, right, in one of these bearers, and can be impacted by modulations in the channel, resource block issues. So being able to kind of analyze that at that kind of granular level helps you eliminate whether the RAN is at fault, or, you know, whether you've got a good RAN that might be somewhere else. You know, here, for example, I'm just showing that you know, the modulation aspect of a network can have a major effect on the service you've got. You know, low modulation issues can produce low data throughput, have an effect on latency, and that overall has an issue on service quality. So the whole kind of RF environment really needs to be taken into account when you're thinking about the kind of end-to-end area. Then if we start from the kind of user device and kind of work into the network, so being able to really look at kind of user setup, being able to kind of test that, look at, for example, like bearers getting set up. So for example, here we can even see the bearer setup, like the default bearers and dedicated bearers getting set up. We mentioned, of course, this QCI equals 1, the importance of that. Being able to kind of analyze that and show that it's being set up. We mentioned kind of IMS signaling, for example, gets a QCI of 5, so you want to see that's got set up properly. You want to show that the kind of SIP's getting set up correctly. So all those sort of things, you know, going from default bearer to what's the SIP signaling is the actual voice traffic getting the bearer that it requires in order to deliver the service. So, you know, you can do some of that capability from capabilities on kind of handset testing from the actual user device. And then Steve, we talked about voice quality. Steve talked a lot about voice quality, R-factor, MOS score, PESC. Now Polka has been defined and is often gets used, and really being able to do testing from a handset to a handset gives you the kind of opportunity to exercise the whole network, end to end, including the IMS infrastructure and the core to set that up. And accuracy here is very important, because an average value of voice quality is not going to give you the information you need. You can have a 10-minute call. The first 5 minutes were terrible. The second 5 minutes were great. So your average measurement it's average, but almost certainly the user experience of that has not been good. So you need to be able to be reporting at short intervals to get that accuracy through the whole call, be able to exercise the network and get a full kind of end-to-end view. As well as doing that, interoperability is important here. We get involved a lot in kind of Plugfest, for example, for doing kind of interoperability testing. So verifying the VoLTE service on demand, looking at the protocol analysis of the control plane and the user plane, correlating that information together, being able to potentially get the voice audio extracted and played back. Looking at compression, and also an important thing is being able to look at VoLTE as well as other kind of IMS-based services. That becomes a kind of important part of analysing VoLTE, particularly when there's multiple network element providers involved, and making sure that the whole kind of standard of the service is delivered as it's meant to be delivered. And then if we just look at other kind of parts of the network, the location intelligence part of VoLTE calls, I think, becomes a very important aspect as your users start to take on the service and you start to kind of build that up. So getting kind of surgical precision to where you've got some specific VoLTE hotspots, because they might not be the same as your other voice hotspots, and they might not be the same as data hotspots. So location intelligence allows you to locate, store, and analyze all your voice calls, giving a real rich information to help you look at network performance and overall enrich the user experience. And getting that information from a customer-centric perspective rather than just a network perspective becomes important. So you can profile, for example, around VoLTE failed calls. Look at the QCI code, look at calls that failed. You could have a location intelligence system that's across 3G and LTE, so you can actually look at handoffs. Going from LTE to back to 3G and back again to determine was there a voice quality issue there? Did things get dropped there? Are there problems there? Where am I having issues around VoLTE particular calls? So getting location information around the voice service becomes really important. So look about kind of interoperability, location intelligence, the RF aspects of it, pre-deployment testing. Now Steve's going to come on. He's going to talk a bit more about the whole kind of customer experience assurance and how you might want to do some analytics around that.
Thanks, Paul. Yeah, so I want to talk a little bit about the JDSU Excite customer experience solution. This is a new solution that we just introduced to the market last year. We're very excited about it because it really brings a new value proposition to the industry. And in particular, what it does is it breaks the cost relationship that applies to traditional assurance solutions. A traditional assurance solution, typically, the cost of that solution will grow linearly with the growth of network traffic. And with network traffic essentially growing exponentially, the cost of such traditional assurance solutions is becoming uneconomic. With the Excite solution from JDSU, we've been able to break that linkage between traffic growth and cost, and we've been able to demonstrate that in real-world network deployments over the last 12 months. And now this year, we've taken that fundamental platform and we have added to it VoLTE and IMS assurance capability. So that allows us to take that excellent cost profile from the platform and deliver a specific VoLTE customer experience assurance workflow in a highly optimized way that is tuned specifically looking at not only VoLTE control plane but also VoLTE user plane and doing RTP analysis. And so this solution works across both control plane and user plane, looking at some of the interfaces that we've talked about already, including across the IMS, but also looking, for example, at the RTP, at the S1U interface, at the proxy CSCF. We also look at the SIP control plane on the GM interface between the UE and the PCSCF. So the ability to look across the whole of the VoLTE call in the EPC through the IMS and being able to then provide a correlated view of what's happening there provides deep insight into what's happening with the VoLTE service. But not all service-affecting problems have the same impact on the subscribers, and so the VoLTE-specific workflow in Excite lets you see the scale of the impact of the problem, which allows service providers to prioritize the issues having the most impact on their customers. And you can see some screenshots here on the slide. Excite incorporates a highly graphical, intuitive workflow that's VoLTE-specific that provides multi-dimensional analysis of problems in an integrated way that maximizes getting to root cause identification as quickly as possible. One of the tools within the workflow that, in the Excite workflow that allows us to do that is what we call the tree map, that graphically shows not just what the problem is or where the problem is occurring, but also shows the scale of the impact of the measurements and the KPIs being analyzed. So this isn't just saying that a KPI crossed a threshold, it's providing an indication by the size, the relative size of the segments as to the scale of the problem that allows you then to prioritize which issues that you go and address first. Excite also includes a best-of-breed diagnostic application based on JDSU's deep experience in the LTE, VoIP, and IMS assurance domains that we've been in from a monitoring perspective for over 15 years now. The real breakthrough with Excite is, from a VoLTE perspective, is the workflow that's built around that multidimensional analysis of KPIs and that minimizes the amount of issues that require the use of the diagnostic tool to get to the root cause. So that workflow highlights the issues causing the most impact to the subscribers and also allows you to quickly identify what happened, where it happened in the network, and why. And with that, I'll hand back to Paul for some closing remarks.
Great, thanks, Steve. Yeah, so look, thanks everyone for listening to this so far. Hopefully, you've seen both the benefits and the challenges of VoLTE, and really what's needed to ensure that optimal service end to end. VoLTE is expected to deliver about $2 billion for operators by 2016, and as a foundation for operator differentiation, VoLTE, I don't think we all agree should be left to chance. So let's now go back to Kyle, and we'll do some Q&A, Kyle, if we can.
Yeah, absolutely. Thanks, Paul. Yeah, we've had a number of questions come in, and again, anyone, please submit your questions to the questions panel, and we'll try to get to them. There's also been a couple of notes about the handout. As soon as this webinar wraps, we will send an email out to all registrants with a link to that JDSU handout. So the first question coming in is, can you provide more information on active versus passive voice quality?
Yeah, I can maybe cover that, Cal. So if you think about the PESC and Polka capabilities, allow you to inject an audio kind of file into the packet, send that out into the network, and bring it back around to the other side, and then you can do a kind of reference test against what you sent out. So if there's differences, that can help you produce that PESC or Polka score. So that's typically an active test when you're actually specifically putting a waveform in, sending it out to the network, coming back and looking at the result. With passive testing, what you're typically doing is you're monitoring the network, could be any place in the network, and you're looking at the packets and determining from the way that the packets are being sent, you know, from the latency and jitter and packet loss, etc., you can create this R factor MOS score, which gives you again a service quality. So it's not that factor is not looking at the content of any audio file, it's looking at the network's ability to deliver that packet, and hence the effect that has on voice quality. It's interesting actually that in a lot of the kind of testing environments we've looked at, there's quite a lot of correlation between your R factor MOS measure and your polka measure, which is kind of what you should expect, but it's quite often good to have both.
All right, great. Next question we had come in is, could you describe a little bit about the exact differences between VoLTE and voice over IP?
Yeah, maybe.
Yeah, go on, Steve. You go.
Yeah, I would say that firstly we can say that VoLTE is a VoIP service, but not all VoIP services are VoLTE. So VoLTE is a VoIP service because it's IP all the way to the handset. And so that makes it a VoIP service, but there are a broader range of VoIP services covering both mobile technologies and fixed wireline technologies that are available, whereas VoLTE has got a much more standardized approach through the various 3GPP standards that have been made available that describe in detail the functions of the network elements, some of which we've talked about in this presentation, the interfaces between those elements, the protocols that run in those elements. So VoLTE is a more standardized service at this point in terms of its implementation compared to VoIP services, which, as I mentioned before, we've got more than 15 years experience in this space. There's a whole diversity of different protocols out there, including legacy protocols like the H323, H225 family of protocols that have been used in the past to create VoIP services, whereas now VoLTE is much more standardized, for example, around the SIP protocol.
Yeah, and that's good, Steve. Just a couple of points I'll add to that. And Steve's right. I mean, VoLTE is designed for mobile networks, so as has a mobile component to it, which most voice over IP, well, in fact, all their voice over IP protocols don't tend to do. And the other thing is, and I think it was in a Signals Ahead report, did some analysis of comparing, for example, like Skype calling on a mobile versus VoLTE calling, and everything was pretty fine from a kind of voice quality perspective when you had a cell site that wasn't loaded. But when that cell site had any kind of loading on it, so other people are doing data services, the Skype call voice quality went down hugely. But of course, because the VoLTE call has that guaranteed bearer with a guaranteed quality of service, the voice quality of that stayed up. So I think that's a kind of key aspect of it. When cell sites are busy and the network's busy, you continue to get the voice quality on your or you certainly should, I should say, get the voice quality into your VoLTE service, assuming that everything's working well, which you typically wouldn't get with just a traditional voice over IP protocol.
All right, that was a great answer. So the next question we had come in is, for LTE systems with carrier aggregation, can VoLTE go through the secondary component carrier, or should it stay on the primary component carrier?
Okay. Yeah. Interesting question with carrier aggregation. So just for everyone else's benefit. So LTE Advanced includes kind of carrier aggregation where you can use multiple kind of carriers combined to give a kind of a bigger amount of bandwidth. Now, the interesting thing about kind of VoLTE is VoLTE in itself, of course, doesn't necessarily need a lot of bandwidth, but it does need the guaranteed bit rate and quality of service associated with that. So it's a lot more around jitter and delay than overall bandwidth. So to be honest with you, as long as the bearer is set up to deliver that quality experience, the particular kind of carrier over it shouldn't really matter if it's not been particularly affected. So you know, I'm not an expert on that side of things, but I don't think it should have a big effect.
Okay, great. Next question we had come in: how might one use RAN and core data for end-to-end solutions?
Okay, yeah, let me touch on that. Stephen can come in. That's an interesting one because, so for example, like at JDSU, we have location intelligence information with our Arizo Geo platform, and I touched on that earlier on, looking at kind of VoLTE hotspots, calls failed. And then Steve's talked about Excite, which does core-based, analysis, database in the kind of core part of the network. Of course, having both those capabilities gives you a real kind of end-to-end network view, because you get basically you get all the kind of call location information from the RAN, from Arizo Geo, and then you get the kind of app aware and call setup data service information from the core. So being able to kind of combine those to show a kind of end-to-end view gives you kind of really unique visibility into the voice service. So I think that's an interesting kind of development in the way things are going to be able to kind of analyze services. And of course, given VoLTE is that kind of real-time service, getting that in real time is a crucial component as well.
Okay. Next question we had to come in is, does VoLTE actually use the LTE 700 megahertz bandwidth, or is this just a name used to indicate a different way to process information?
So say the question again, Kel. Sorry, I just want to make sure I've picked it up right.
Yeah, no worries. So the question is, does VoLTE actually use LTE, the 700 megahertz bandwidth, or is it just a name used to indicate that it actually processes the information differently?
Yeah, I mean, VoLTE just ends up being, really another LTE data service. So the frequency that's applied to that from an RF perspective doesn't matter. It doesn't really matter at all. I don't know if that's answering the question. I apologize if it's not.
Yeah, that sounded about right. So we have time for probably just about a couple more questions here. So next one is, what is the #1 cause of poor voice quality over a VoLTE network?
Steve, you want to take that one?
Yeah, I think it's hard to say that there's a single most dominant factor at the moment. From our experience, we're seeing that there are a number of issues that need to be addressed. In some of the service providers that we're working with, they see a particular issue, for example, with one-way audio, that being where if we've got a called and calling party, the RTP stream in one direction is successfully established, but it's not successfully established in the other direction. And that tends to be an issue of interaction between the network elements, and in particular, getting confirmation that the bearer has been established successfully. So we're seeing a number of issues at the moment in our early deployments that relate both to control plane issues between network elements. As we've described in the presentation, there are a large number of network elements involved, and as this service is relatively new, there's often frequent updates to the software loads on those network elements, and keeping those in sync and being able to operate together is an issue, particularly when many of the network elements have a heterogeneous component to them. There are multiple vendors involved. So we're seeing, on the control plane side, we're seeing that. We're also seeing issues in the setup of the bearer paths and also in the maintenance of those paths during the duration of the call.
Yeah, and that's good points from Steve. And as Steve says, the whole kind of end-to-end chain. I think one of the problems operators often have is, if voice quality does get degraded, it's where is that? Because it could be in the RAN, it could be in the backhaul, it could be in the core, it could be signaling, it could be user. So I think that being able to kind of identify where in the network might be causing the issue is a problem. I think the other thing is handoffs to networks is another crucial point. And I know a lot of operators are concerned about that. If you move out of an LT coverage, you need to hand the call off to 2G, 3G. The possibility of the call dropping. during that, or not connecting right, and issues associated with that. So I know that's certainly a kind of problem in a lot of people's minds.
All right, thanks. So we have time for just about one question. So next question is, can you discuss a little bit farther about the rollout for the Excite solution for VoLTE and when it would be available?
Yeah, we have to take that, Cal. Yeah, we are in active trial deployments now with leading service providers. And so this is a solution that we are able to bring on site right now in terms of being able to do trial deployments, and we will have a full production rollout later this year.
All right, thank you. That's about all the time we have today. I want to thank everyone for attending today's webinar, VoLTE, Don't Risk Short-Circuiting Voice, presented by JDSU. Again, our presenters today were Paul Gowans, Solutions Marketing Manager at JDSU, and Steve Barnes, Product Manager for VoLTE and IMS at JDSU. All right, thank you, Steve and Paul.